Hey everyone, and welcome to this explainer on CNC technology. If you're an engineering student or a manufacturing professional, you are absolutely in the right place. Today, we're mapping out the what, how, and why of modern CNC. We're going to cover everything from the massive machine architecture all the way down to the raw code that commands it.
Here's our game plan for today. We'll start with what CNC actually is, peek at the hardware inside the machine, and then get into the programming. After that, we'll hit CAD, CAM, and simulation, talk about physical operation and quality control, and finally, look ahead at the future of smart manufacturing. Let's dive right in.
All right, part one. What exactly is CNC technology, and where did it come from? So, CNC stands for Computer Numerical Control. But simply, it's the automated control of machining tools using a computer and specialized programmed code. Tracing its roots back to MIT in the 1940s and 50s, this technology completely revolutionized manufacturing. It replaced incredibly intense manual labor with standardized code, allowing machines to automatically execute complex, precise 3D movements.
Think about the massive leap from traditional machines to CNC. Instead of relying on manual measurements and the physical skill of an operator, CNC completely automates dimension control. It uses continuous feedback loops and high-stability servo motors to achieve mind-blowing precision and efficiency. It really is a night-and-day difference.
Okay, let's move to part two and look under the hood. Let's talk about the hardware and systems inside the CNC machine.
To understand how it works, you have to look at the data flow, which is basically the brain of the CNC system. The part program feeds into the data processing unit, which then sends signals out to the drive motors. But the real magic, that's in the feedback mechanisms. They send location data back to the control unit in milliseconds, ensuring the machine literally never loses track of where the cutting tool is.
Translating that digital brain to the physical world, you get some incredibly heavy-duty hardware. You've got the rigid machine structure, the spindle holding the tool or the workpiece, and the X, Y, and Z feed axes, driven by those precision motors. And right there on the side is the CNC control panel. That's the operator's direct interface to the machine's brain.
Out on the factory floor, this technology generally takes three main forms. You have CNC turning machines, or lathes, where the workpiece spins, CNC milling machines, where a spinning tool cuts into stationary material, and machining centers. These are the heavy hitters that combine milling, drilling, and rotary axes with automatic tool changers to absolutely maximize efficiency.
Moving on to part three, programming the process. How do we actually speak the machine's language?
Seriously, think about this for a second. You have a massive machine capable of ripping through solid steel. How does it know precisely where to go to an accuracy of 1,000th of a millimeter and exactly how fast to get there without breaking anything?
The secret sauce is G-code. On standard control systems like Fanuc, movements are commanded by the letter G followed by a number. G00 is rapid positioning, moving as fast as physically possible without cutting. G01 moves in a straight line while actually cutting the material. And G02 and G03, those carve your arcs and circles. These specific commands are literally the foundational vocabulary of modern manufacturing. But here's the catch. Coordinates are totally useless without a starting point, right? Every CNC machine has a fixed, absolute machine zero. Programmers, however, use offsets, like the G54 command, to mathematically shift that grid directly onto the raw material. This creates a highly practical starting point called workpiece zero.
And this leads us to a crucial programming strategy, absolute versus incremental coordinates. Absolute programming plots every single destination from that fixed workpiece zero. Incremental programming, on the other hand, plots the next point from wherever the tool is currently sitting. It's kind of like the difference between saying, go to the exact GPS coordinates of the grocery store, versus just saying, go 2 blocks forward.
Part 4. Let's talk about the digital thread, CAD, CAM, and simulation.
Let's be real. Nobody is writing incredibly complex 3D G-code by hand anymore. Instead, we use a digital thread. It starts in CAD, where we design the 3D model. Then it moves to CAM software for setup and tool selection. The software automatically generates the toolpath. We run a simulation to check for collisions, and finally, we output that perfect G-code program to the machine. I cannot stress this enough. Simulation is absolutely non-negotiable. A CNC machine will happily drive a spinning tool directly into a solid steel chuck at rapid speed, causing tens of thousands of dollars in damage in a fraction of a second.
Simulation prevents those catastrophic crashes and eliminates material waste entirely in the digital realm before you ever cut a real part.
All right, part 5. Taking it back to the physical world. Operation and quality control. Out on the shop floor, the setup workflow is super strict for a reason. First, you have to securely clamp the raw workpiece. Next, you install the specific cutting tools. Then, operators manually touch off those tools to set the work coordinates and tool offsets into the control panel. Only then do you load the program, run the machining process, and finally inspect the finished piece. And hey, the job is definitely not done just because the machine stopped moving. Operators use precision instruments like micrometers and coordinate measuring machines to evaluate the part. They check for strict dimensional accuracy, service finish, and geometric perfection. They also have to constantly monitor tool wear and edge chipping, updating offsets to ensure part number 100 is just as perfect as part number 1.
Finally, part 6. Let's zoom out to the big picture and the future of smart manufacturing.
Welcome to Industry 4.0, folks. Today, CNC machines are no longer isolated islands sitting in a workshop. They are deeply integrated nodes in a data-driven smart ecosystem. They're being loaded by automated robotic arms, they receive their programs instantly over CAD/CAM networks, and they stream real-time production data right back to smart factory servers.
So you've now seen the entire bridge from a digital design to a physical part. G-code, CAM, and simulation. These are truly the foundational languages of modern manufacturing. But as AI and robotics continue to take over the factory floor, I'll leave you with this question. Will human engineers soon be the ones programming the machines, or will we just be supervising the algorithms that do it for us? Thanks for joining me for this explainer, and keep innovating.